LSST and also some local volume cosmology, right?
Right. Thank you, Rogerio. It's a pleasure for me to start here. I will start with this small review about our activities, our participation in the great collaboration, works at Córdoba. I will talk later about this. These are my coordinates. And Córdoba is in the center of the country. It's the second largest city. This is the Córdoba Astronomical Observatory. It was founded by President Sarmiento. He convinced this guy is Benjamin Gould. He was the first American with a PhD in astronomy. He studied with guys. And he was the director of the Naval Observatory when Sarmiento was the ambassador in the United States. He convinced to come to Argentina and run and build up the first catalog of the southern sky. It was 150 years ago. This was the product. And in some sense, Peter Rubin continues this task. And this is why one of the reasons we are interested in it, of course, is mainstream project. We have a participation group led by Córdoba, but with a lot of most of the astronomical institutions in Argentina, which are over there, most of them in Buenos Aires, but also most of the people is from Córdoba, and also there are people from San Juan, which is my home, where there are all telescopes there. Actually consists in 12 PIs working in the 8 and still scientific collaborations. We have a place to grow, but we are experiencing some troubles. We'll talk about this because we are funding through individual grants. And our income consists of software development and telescope time. Our projects have suffered the current crisis. We have recurrent crisis, economical crisis in Argentina. We have annual meetings to share progress and activities. Our team of developers, there are two people there, Marco Franchetti, Carolina Villalon, she's participating of the other machine learning workshop that's running on these days. They work with the better proving the speed, producing the notebooks, and actually they are working with the SciComm team, developing script for working the things. This is our main contribution. This is personal of the team. Also, there is time in this small telescope. I spent the past decade trying to build up around this small telescope aimed to detect optical counterparts of gravitational wave sources in a very nice site near the site of qubits, which is near there. This is more to the west in a very high altitude site, which is really incredible. But there are many difficulties to run the site there, and the telescope is right now moving. But it's moving to San Juan, where most of the telescope are there. They are sort of contribution on a small telescope, which are complementary to Rubin. This is a telescope from the Buenos Aires group. And also we have some time in this deep space antenna from MISA, which is located in southern Mendoza. And it is useful for radar for near objects. Maybe in the future it could be used also the JAMA antenna in the north of Argentina. All these projects are suffering the lack of funds, the current lack of funds. Therefore, possible maybe should be cancelled. But also there are a group which I participate in, which is led by Mathematics, which is well known here, trying to do follow-ups for microlensing sources. And there are also a very nice contribution for Fermilab. They have this new kind of detector, the Skipper CCDs. There is one to be installed on this 2-meter telescope. It's the biggest one in Argentina. We have also a small part on Gemini, and this opens a lot of opportunity to astronomical follow-ups of the amount of alerts that LST will produce. Also, we hope to could build up a little dialogue for analyze Rubin data. We have a lot of experience and we have software for different kinds of analysis. I will talk today about correlation functions and detection of satellite and streams. In the local environment, we have a number of, they are becoming all the computers in Argentina. We also, if you have many problems with this, we have a lot of experience on machine learning because we created a specialization on data science and machine learning there in Córdoba a few years ago, mostly working with the industry. Okay, part of the norm meetings and our participation group, we invited Rogerio, Timonita, and other people from South America join us, people from Mexico, and we start this nice series of meetings. We celebrate the first one on Serena past June. Was very interesting because we will visit the real scene. This is the Concan camera and the faculty chamber. We have the full Chilean experience. We have a headlight on Monday and fruits on Thursday. But against all the odds, the meeting was very nice. This series will continue this year on Mexico, on November, I think, and next year in Brazil. We hope that they could join all the astronomers and physicists participating in Latin America and Rubin Observatory and could share experience and collaborate. Okay, let's see. I will talk about our work. I work on statistics. I will talk today about I coordinate these 4 groups of research. I will talk today about some works on precursor data for LST, mostly on software developments, on infrastructure, and some work we are doing on the local environment, mostly with Gaia, and right now with HSC. This is our small group on large scale strategy. Claudio Lopez is a student, Professor Emilio Donoso at San Juan, in my hometown. We're working on correlation functions, and we have the lab funded by the Steel Discovery Alliance to collaborate with this amazing team, the LSS frameworks team, which is located part on the University of Washington. We collaborate with the branch on Pittsburgh, Carnegie Mellon University. This is a kind of Avengers team of software development. It really is an amazing people. And actually, the team was in Kubica, and a lot of these people collaborate with us. It's amazing to work with them. Most of the developments were well, actually, the picture is trying to compute, all about this correlation function. The point is correlation functions need to compute distance within 5 points. The points are galaxies on the survey, and also points are comes from the random points generated in the exact area and volume. This relates with the selection function. In particular, the angular selection function, also selection function attractive, which would use the fundamental attractive. This involves a lot of computation, which is kind has n squared. Of course, there are a lot of procedures to improve that, but essentially it's a problem when you go to billion of galaxies like an LST. And it's a problem for us because we don't have big computers. That therefore sorry.
And why don't you use 3-core, for instance, to do that?
Yeah, we have an alternative code, but okay. do the same thing. The idea was try to compute the distance and improve how runs the codes using this amazing schema, which is a schema for theoretical tiling of the sky. It's very smart. I recommend if you don't know about this HATS package, was rebranded a few weeks ago, and LSTB, because there are developments of the LINCSI team that allows you make a lot of computation easily, basically, because you are doing computation in this distributed manner based on task. That's very easy to learn because the primitives are the same as pandas, Python, wrote code and standard Python code. And also LSTB put all the structure in packet file, which you could easily access just one column, and this the task very fast. The idea is to make partition of the sky and you put high resolution where most of the data are. For instance, this is the Gaia density, stellar density map, which is the order of billion of source. And actually, there are a lot of sources, obviously, on the plane and on the Porsche. And therefore, there are more pixels, smaller pixels there. And this allows you to make easily cross-matching, for example, in a lot of sources in a few minutes. This is the best way to don't use AstroPython. But that LSTB and HATS are the answer for that. And the idea was try to compute the correlation function using this scale. And this led also, talking about mass, there are a lot of defects on the image. The most important comes from black stars. Here you will see the size of the defects, different defects introduced by the stars as a function of magnitude. And this affects strongly, depends obviously of the optics, but this affects strongly the area where you could do real computations. Typically, you need to mask these regions. If you put a strong constraint, you could lose 30–40% of the area of the subject. That's not the idea. But the point is, you have this problem in every single catalog or survey. We tried to do a code to mask. There are two historical approaches. There is an old one, which is Kalimangan, which is great. I used this when I was a student. And it's a low one, which is based on the spherical polygons decomposition. But people right now prefer to use helpix, and actually STD and HATS use helpix under the code. We tried to create this, we started to create this package, which is called Zorro. And the main idea is not just distribute the catalog, distribute the mass. And the mass is hidden in the mass plane of the image. I'm thinking in the future, try to distribute the full mass, including, cosmic ray and small defects to the community. This is because the vision is the people turning from computing using catalogs to pixel level computation, like has in weak lensing. The people are doing this right now. And therefore, you need a way to distribute the tiled angular mass. Well, this is work in progress. Actually, there are a lot of technical details here, but actually it works well. And the main idea behind is the concept of multi-order continuous map. It's interesting because you could create easily mask we made for HSC data. For instance, this is a small part of the sky. You could see here the multi-order, different orders of hair pixels, right? And this is the mask for around very bright star and other stuff. And you have this kind of effect everywhere. Because
Instead of more similar to Celtics, it's more similar to HUDs that you introduced before. Because I see.
Yes, that's it, works over the things,
Yeah, I
right?
understand, but I see from here that you have different sizes. of
Yes, exactly.
them.
I will come back in a few minutes. But for instance, for all the HSC special program footprint, you can compute in a few minutes using basically, the modern supercomputer, right? And that is nice, because it's interesting, but we don't have really, this is a problem because the masks are not really available, When you try to reproduce any result, the people don't share the mass. There's not a unique form to share. It's a kind of secret sauce of each collaboration. And especially on HSC, we can obtain the angular mass. This is why we try to compute using software. HSC, a lot of people talk here, but it's the most near moving like survey available today. Comprise these red areas and these blue ones in the white version, which is the most interesting, and have 500 million of source there.
So in the data release, they don't release the masks?
No,
Oh,
you need to build that from scratch. I think it's the same everywhere. I have the same situation in other times with 2DF slow, and I don't know how it's in this, but really the people don't share the mask. It's strange, but if you need to reproduce the computation, you need it. Yeah.
I think it's difficult to share it, at least for the case of DES, because it generally discards pixel depending on the systematic correction.
Yeah, there depends a lot of your selection. I will talk about this.
On the analysis.
Yes, exactly. This is why we don't have a point of comparison against Surfer right now. Therefore,
There is a public. This is one thing. Make sure that there is
yes, there are two versions of the mass, but you ask for them. They start. Okay, I can live with it. This is why Surfer, our main character, has a split personality. Diego de la Vega is a kind of alter ego of Surfer. He's a kind of Bruce Wayne on the California of the 19th century. If you don't remember the show, I saw this when I was child. But how we don't have point of comparison, we start to think in a simple way and develop this package, which is called Skakatan. This is we finish it right now, and the idea was create a mask in a pipeline way. It's interesting because you could define very well the stage, how you are building the mask, all the people could reproduce, and would apply this for Robin or for other characters. That's interesting, and this works Excel really very well, and also allows you to generate random points inside the mask. That's interesting. This very flexible, was designed for HSC, but all the accumulators are very nice. It still probably don't scale very well to the LST scale. It's something that we are testing on more catalogs right now. Okay, how this works? Essentially, works over Spurs. Spurs is an amazing package, only by people from Princeton and from the Space Telescope Institute. And actually, the idea is very simple. If you have some objects in your catalog, the red dots, you could first define kind of footprint, the blue pixels, which are from a quad resolution in terms of inside of helpix pixels, and you could put high resolution pixels inside this region and avoid all the rest. This generates a high resolution map, which is very sparse, with all log sparsity of this because computation are very fast. And this typically are the orders. These are the inside orders for all this. Depends on your density or your catalog. which are the kind of effects. But eventually, and this is the interesting part, in El Zorro, we would like to go down to 21, which is sub-arc-second resolution. And that's interesting because in the future, right now, all the people are developing neural networks and deep learning to detect cluster, make measurements of wavelengths, detect gravitational lensing, whatever. And therefore, you need a way to distribute not just the image, also the angular mass in an easy way. That is why we are doing all this work. Okay, how SkyKatana works. This is the first point is you need the HATS catalog. It's very easy. Also, the Lindsay team distribute a lot of catalogs in this format. Gaia, DS. One, I think HC we need to put there, but there are many catalogs working on this. And this is useful. You could do cross correlations, cross match very easy. Okay, doing this, you catalog, you decide which is the higher order of your angular mass. This is basically define your footprint of the angular mass. These are the stages of the SkyKatana. After that, you could apply the details of how you select your sample. For instance, this we are working with the coats, and therefore, in the borders of the footprint, you don't have, for instance, the same number of collapse in order to reach some given magnitude limit. And therefore, we could eliminate this and make similar logical operations in order to have the condition in all the bands that you're considering in your cap. This is a very simple way to build up maps and make reproducible for all the people. Okay. Okay, the holes. Okay, pick up Gaia, for instance, you need the information. This depends on the telescope. Could be even radio telescope. And these are the holes. Here I show the random points generated in the holes, and I'll show you how this is in the tailored, how is the tailored mass. This is bright star and other smaller ones. Also, we could add, that is important for a larger scale structure. There are many nearby galaxies, which at least the old version of the Rubin diagram separate in several sources. And you don't have a cluster of high energy quasar, you have maybe a number of start from regions or global cluster around a very nearby galaxy. Okay, there are problems at very near, but there also is interesting because there are a lot of these galaxies we found in HC, and actually we are using the same codes in order to compute the halo occupation of these galaxies. And this is competitive with other surveys because this is an 8-meter telescope. Finally, using all these defects, other ones you can add, this is very easy, it's configurable. You finally have this small area. You have a combined mass. Here I generate the random points inside the area, which we use for compute correlation. This is not because SkyKatana really run, we could build up a very competitive mass, 40 seconds in a lab. And inside the order 16, and this is very easy, reproducible, and actually, which is the main difference? Well, SkyKatana, you don't need a lot of resources, but in Zorro, it will be necessary when you go towards to the full Rubin cut, right?
And
See,
the
yes.
mask you're talking about, is it each pixel has either a 0 or a 1?
Could have a different levels of mask. Actually, we are using binary, but it's very easy and it's extended. Also, in the case of Zorro, we have all the defects, different defects has a different number of ordering. value for angular mass. But you will select the type mass. That's a final idea. It's not finished yet. But actually, it's just add a few bits to the angular mass to do that. Okay, we have this all code. We have a long tradition of correlation function computation in Cordon, as or boss was working with GPUs on the old days. Now we have this code, which is made mostly by Emilio Donoso, which is Gundam, which compute all the angular correlations, cross correlation, three-dimensional, and whatever is written in all fashion for them, parallelized with OpenMP and MPI. Was really very well. The idea was first remount this. Actually, it is very installable with the standard read-dogs and all the stuff. And the other point was translate this code and use over LSTV and CATS in order to improve the computations in the future when we have billions of racks.
So sorry, then the previous code computes a pixelized version of clustering. So
The other, the previous code compute
Gundam.
the mass.
No,
Gundam works with Gundams.
both directly point and both
Yes.
brute force.
Yes.
So do you have like, at least as Carlos says, like a comparison with how it behaves like with 3-core or with other?
Yeah, it's comparable, right? Actually, it depends of exactly the sample that you are using, but it's competitive. It's very competitive. The idea was try to produce a code that compute correlation function, basically distance and meaning, but working over LSTV and CATS. That's the idea of code. This is work in development. Actually works, but it's working, but it's in development yet because Gundam works better. They have a lot of optimization in place. But we hope this is just in a small area, hundreds of square degrees. We are testing how this is scaled. That's the difference, right? When you go to billions and lots of square degrees, probably this will improve. Right now, the big difference is caused under the hood. The computation is using task. And all the distributed system, or do the real computation, Spark or even TensorFlow, have the master algorithm that computes a direct acyclic graph, which is the important part of how you distribute the computation. And the graph or correlation function is too large right now. We have a solution which was proposed by people from LSS, which is trying to use a MapReduce schema under the hood. But practically this means that we should change task to Spark at some point. That is a decision that maybe should make in the future. But actually we are working on improving that and testing how this is scaled for bigger areas and more deep catalogs. That was done in single mode catalog with, and we are trying to recover the tiny correlation function right now. This is work in progress.
And around how many points are you using for the catalog?
For this,
How many cats?
100 minutes. Okay, but we are trying to do science in meanwhile, and we are, for instance, doing correlation between energy galaxies and HGC, because there's a well-known sample with both photometric redshift. Also, we are planning the idea to see the computation of the correlation function is reduce or improve the correlation redshift. That's work in progress. This is new student working on that. And also we are doing correlation with this GM, but really are clusters which is great, was made using Gaia and WAS photometry. Really, it's very nice catalog. Here you could see the small scale. Here are the redshift distribution. We are doing real computations and real cases. My collaborators in San Juan are very interested on AGNs. And actually, this is a result, for instance, of the cross-correlation between quagga and LRGs, and is really comparable to this new determination from Rosado et al. It's a very recent determination. They made the AGN sample using data from HC and also spectroscopy from this. And we are very interested in this particular sample because they say that there's some difference between the quasars and the dust obscurity AGNs, and we can find this, and we are trying to disentangle this. We have mostly quasars. We are trying to find the AGNs on HC. There are many ways to make cuts on the color magnitude diagrams, but we are trying to use, I enjoy very much to work with the IATE, this new foundational model that recently was published. And also, I'm very interested with one of the students to do calculation and quadratic with thousands. Someone asked this on the Rubin forum a month ago, and nobody answered that. And this.
How do you get to how do you find the AES, the obscure AES? Because you said that you didn't purpose it, but if they are obscure, I guess that they are not obscure in one of those two samples. Or how do you find that?
Yes, let me explain which is the isotropy model.
Oh.
This is a kind of foundational model. It's like chart, GPT models, right? It's multimodal. It ingests image and spectrum, for instance, like the multimodal models, ingest text and image of different classes of inputs. They pass through encoders, part of the computation, but they give us a method to align the concepts that you have to go through the two encoders in the same latent space. Also, it's interesting when you align this, you collapse, for instance, okay, I have this image of the galaxy, which is a spectrum, and these are the prediction of the model. And it's very interesting because you could recover very well the spectrum, the training sample, obviously, but actually you could apply, if you know the spectrum, you know the redshift, the stellar mass, the photometry rate, the vitality, and so on. And therefore, it's interesting for you to find AGNs using that. And these are upstream tasks, and they are very easily computed because you just add a few layers to the neural network, and it's very easy. And also, we are interested in compute corrections using that. We are testing both ideas and working on that.
You need the spectrum.
No, that's the point.
Okay.
That's the point. You need for training the spectrum. I made a sample for training this using HC galaxies, which I emitter telescope, and this is spectrum. We are retraining. Okay? That's a huge computational task, but they're doing a kind of transfer learning in order to download the nodes. But the important point here is to start with image like a Rubin and could predict a lot of properties using this model. We are trying, this model was trained with legacy data for the telescope, the spectrum mostly from the slow. We are trying to improve this using emitter data in this spectrum. And since we have the classification between dust obscured or whatever, we could make a specific output in order, okay, I give you the image, you know the spectrum on the open space and say if this is idea obscured or not. That's the idea. Also, we are making the test. This is one from Jeremias Rodriguez, one the new student of computer science. And we are making correction. So that's very interesting because the standard way is use the random code. This is all one was trained on, was built up on slow data, what are very low prediction. What are the difference between the Gladstone estimate and the real gap correction computed using the spectral, the aperture correction and all the stuff, okay? And these are the same using a computer. Something the same, but the difference, okay, is most or less the same. Actually, they are much better, it's more symmetrical, but the point here, you need to add as data the redshift. But in photometric catalog, you don't have. And if you use the photometric redshift, this goes widens and doesn't work. And therefore, you don't know how to correct even a low redshift when the sun is. And this is important even more for high redshift. Well, that is why we are training this right now. The message is, okay, multimodal models are very powerful and could be used for downstream tasks very easily if you train well. This is interesting line of research we are doing right now. Okay, also we could build up angular mass for cross-matching, cross-correlation between samples, for instance, in optical and radio. We are using one of the SKI precursors. And this is the example. There's a lot of single sky. One of them on the HSC equatorial band. And you will see this is the tailored mask for cross-matching. Okay, for cross-matching, we could put redshift to these radio sources, which don't know, and also my correlation and study of people from South Africa helping us with that. And that's important because we are improving in the future in this era, and we have a lot of radio sources.
So why you haven't gone with this horizontal?
These horizontal elements are generated by bright stars that leaves a line of your CCD, okay, due to the radar. How to spin the electrons in the CCD because you have satellite sources, basically. But on this region, you cannot detect anything, okay, in the conventional anything. That is why it's important to learn. And also, if you have something in your radio catalog, for instance, you know, Jupiter, whatever, bright sources, you will without easily. That's what's done in seconds, this computer. Okay. That's interesting because this opened a lot of possible work with other catalogs and use the same tools to do this computation. Okay, and finally, with this, I'm building, I don't know if the first angular mass and right of it's on LST, also Javier Sanchez, but maybe we have the tools to actually compile it. There are different mass, obviously, depends on the science guide. This is for the galaxy, galactic science, but we'll be done for best. And what is necessary is the footprint, the Gaia stars, and the details how the camera works. We are waiting for the ComCam data in order to use that. That could be useful in the future and so on. We do the work, right now you could use Sky Katana for this stuff. That's the longer term. Okay. I will change abruptly from A. Okay, I was talking about galaxies work in progress for LST using HSC, but using HSC is very useful for local volume cosmology. Local volume cosmology, we will talk this afternoon about that, but mostly stand on how much satellite or how many subhalo we have on the Milky Way when nearby galaxies. The Robin will change the horizon. Maybe. And also, that is stellar state. Stellar state, you know, tiles and stars that lives or satellite galaxies, even globular cluster, will move on the Milky Way, the gravitational potential. with Martin Mester at La Plata University, he's developing going to detect this kind of object, detect satellite galaxies or stream, and basically an application of action filter technique. Very well known. Actually, there are 20 stellar streams crossing the HC area. This is just one small part. And that's interesting because this most well, this comes from the Sicilia downstream catalog, and the importance is, the distance, because these are well studied by Guy. There are some streams, for instance, this one, which the origin, this is the orphan stream. Do you know which galaxy guides? And this is interesting because there are a lot of science to do with holes in the streams or breaks on the streams or bifurcation. There's a lot of effect caused, mostly by the presence of subhalos on the Milky Way.
But Mariano, they were discovered by HSC?
Yeah.
All the streams were discovered by.
No. That was discovered using mostly Gaia data, okay, and confirmed.
So they're very local. Then.
Yes, less than 100 kiloparsecs most of them. But the volume of the stellar halo of the Milky Way is roughly 300 megaparsecs. And this will cover
300 megaparsecs.
kiloparsecs, sorry. And this volume will be covered by Rowan. And actually, this small part of the sky is covered by HSC program. Okay, and therefore we are adding a lot of bright stars to this well-known stream and starting this right now. This is one of the things. The other thing I'm trying to identify new satellites is 3 ones were discovered using this data, but I have other candidates, and this is more in progress because one of them maybe is a new satellite.
But their pipeline could discover these streams using only HSC data.
Yeah, right. That's it. And actually, we are testing using well-known streams. That's important for us. We could measure how well we recover the energy. And this is real data. It's not a mock. I have all the problems, even the mask. All the problems regularized due to deal with real data. And that's interesting because maybe it's a small area, for finding progenitor or new features. But actually, you go very deep on magnitude and you add a lot of stars. And if you increase the density of the stellar stream, you can form more data. And this is important for the kind of work that Scott is doing and his team on coming in here. Okay. Also, I mentioned that many nearby less than 50 megaparsec galaxies, which are using to measure the halo occupation using background discount. Background discount basically is count the number of galaxies. We are using the same tools that we would develop for Corti, basically. And this accelerates the computation. Okay. I will turn to another work we are doing. I'm very dancing, you could see, right? Waiting for Rubin, which I was waiting since 20 years ago. Turning to HSC, to learn how to deal with big data volumes. And with the student Keiko Fushimi and Predilecto Mercedes Mosquera and La Plata, they are particle physics by Turner astronomy. And basically, we study, this is it's about the mainstream science and the local volume. It's a particular example, the kind of things we could do on the nearby universe. On the pandemics, I read this very nice paper by Bushman et al. That says something very simple. If you move a dark matter subhalo through a sea of stars, like the stellar halo of the Milky Way, you could detect the F-wave. You could see an increase of density and the velocity fields the stars that go beyond the subhalo moving on the stellar halo. What was interesting, they claim they could measure very well as simulations the mass. And that's interesting because there are a lot of satellite galaxies, more than 70 right now, but in the Milky Way halo, but most of them are very, very small, with very small stars. And also there are subhalos. And it's interesting because you're not using the stars inside the subhalo. You are using the stars in the stellar, in the wake. And this is interesting because this was a theoretical prediction. Nicolas Camargo made a simulation of the merger of the Magellanic Clouds, which is the biggest subhalo of the Milky Way, moving is the orbit. Here is the Magellanic Clouds, here is the Milky Way, this is the dark matter halo, this is exactly on. Then the effect is on the dark matter, but is reduced to the stars. And they actually say that you have this transient wake behind the Magellanic Clouds, this prediction, and also a collective response, because this is a very big subhalo. It's the very right pair, the Magellanic Clouds and the Milky Way cosmological clouds. Right, certainly was an advancement, and the people, Nicholas, try to measure this using Gaia and found it. So that was amazing for me, this paper, and these are the angular distribution in the sky. Here at the Magellanic Clouds, the orbits go over there of the Magellanic Clouds in the sky, and you can see an overdensity on the stellar density of the Milky Way, halo stars behind it. This is the wake of the Magellanic Clouds, and this is the global response. This is data. This is the same simulation of Nicolas that I showed before.
So the Magellanic Clouds pass through our galaxy.
Are moving in all halo. Okay. Maybe there discussion about this the first passage or no. It probably is the first passage.
First pass.
Yeah, but actually,
I don't know that.
the Magellanic Clouds comes with a lot of other satellites of the Magellanic Clouds and globular cluster. This is a family falling on our galaxy. It's the recent minor, maybe major in terms of the mass. Really, it's a big subhalo. But
That is the actual.
it's very low. Very low. This is the stars. This is the star. It's a very low, but it's very
That one you did.
it's extended, right? These are parsec scans. I will show you more plots soon, okay? The point is that they don't measure the mass, and that's where we enter in the game.
So they could estimate the mass of the halo associated with.
Yes, we do. Yes,
Wow.
okay. This is all. We have more tracer because we use bigger sample because in the middle comes the DRT of Gaia. We have I made, this is my fault, I made an improvement. Or not all stars have radial velocities from Gaia, but I made a model, machine learning model of the velocity field of the halo of the Milky Way, using basically the data where we have the 6-dimensional information, proper motions and radial velocities. And it's not so well in terms of the individual velocity of each star, but I don't need the individual velocities. I need a statistical measure. Okay, the stars, they are moved in that direction, the stars, they are moved in another one. Okay, I do this using a normalizing tool. Yesterday we were talking about this for SVI. Okay, these are our results and the points we could measure the mass of the subhalo. This is in terms of the large Magallanes cloud, but really we measured the joint mass because probably the small is a satellite of the large. Okay? But we put in terms of the mass of the LMC, you can see here other determination using internal information, stream, different methods. And the difference here, if you use solely the 6-dimensional information or just the 3D, which are the assumptions about the internal density profile of the subhead. That's when it comes to the interesting plot is this. If you're not
So your measurements are the blue ones?
the blue ones are.
So you really reduced the error bars.
Huh?
You reduced the error bars.
No, because all model is a very simple likelihood, one-dimensional.
I think your
likelihood.
phone is.
Oh, yes, I should finish. 5 minutes. The point is that the model is likelihood in just one parameter. But we improved in the publication of this paper and really don't change if you add parameters like shape of the subhalo, or even now we are including on the paper was published using an assumption of a uniform density map, but the scales are big. Maybe it could be better, and this is dimensional 2D projection, but actually of the size on this in the Magallanes cloud system. The Magallanes clouds are here. Are moving on this direction, the y-axis, right? This is the path orbit in a few gigahertz ago. Let me finish this. These are the overdensities in TV. You know, this is very extended. Initially, we made this computation assuming that it's uniform on this scale. It's not real, but right now we include a 3-dimensional halo profile of the stellar halo, and the results just move a little to lower masses, which is interesting because the Milky Way is also losing weight to the rotation core. The arrows shows the movement of the stars. And actually, you could see, this is the wake, you could see the star moving behind, right? This is the effect of the wake. This is confirmed. Okay? And these are stars coming from the other side of the Milky Way halo, moving towards the Magallanes clouds the global response. Because this really is very big subhalo. The order 10 to the 11. The mass of the Milky Way is 10 to the 12. It's really a very big subhalo. Well, we are making improvements. The important message of this work is, okay, maybe we had a way to measure mass even of other satellites using this. We are running right now. We have before to go there, we have a signal in 3 more satellites of the Milky Way of wakes. I'm testing the selection function. Why we detect in one satellite galaxy and why not in other using the Aurigaia simulations. Really, we could go down to 10 to the 8 solar masses, which is very nearly the limit of the dark subhalo. That is interesting. And actually, the method working with a lot of improvements right now. The other thing, what is interesting, the wake in terms of cosmology, discussing cosmology, is that the size, shape, and the strength of the signal of the wake is strongly dependent or depends of the type of dark matter we are using. These are 2-view simulation made by Foot, which is Tesla, but say something interesting, maybe characterizing the wakes, you could say no, which is the dark matter particle, but at least if color matter, physical matter, self-interacting, or one. That is why we are running comparisons of the distribution of the Magallanes cloud wake. Work by my student, Mariano Dominguez, and the other. We are running comparison of the distribution of the stars on the sky using different spherical polynomials and other projections in order to compare against simulations with dark matter. These the simulations was made by Garavito Camargo. Also, we are using a lot of new simulation that they are constrained simulation. You need simulation of the Milky Way halo, but with the Magallanes clouds moving in. There is a new series by the group of Wessler, which we are using right now. And actually, the point is we need simulations in other dark matter scenarios. Okay, and there was interesting how this connects with the stellar streams, which we are trying to make a method to detect on the new moving data. Naturally, the HSC is the stellar stream show. For instance, this is a very well-known stellar stream, and you see that this split here, there are holes in the distribution. And okay, there are a lot of things that could cause this, you know, for instance, black holes moving on the stellar halo of the Milky Way, the binary interaction, this kind of stuff, interaction with the disk, with the bar, but in the other parts of the stellar halo, it's difficult to find these troubles. And the polynomial statistic of stellar distribution, for instance, along the line of the stellar stream, could say something about the population of that subhalo, which is a prediction of color matter model, right? And it's certainly distinctive how we essentially see on the power spectrum. The power spectrum traduced to the abundance of the mass function of the circular galaxies. And therefore, it's really a good test of the color matter, and we'll say more about this nature. And the important thing on this case, there are a few candidates, GD1, others, is you suspect about the presence of the dark subhalo. Maybe you short term, you can see the dark subhalo, but you could see the trace that lives in the wake. Okay, the star could move behind them, and that and you could even measure the mass of the subhalo. That could be a great confirmation in the future. We hope we are trying to catch or searching, develop a method for searching that halos using the wakes. It's a new technique. We are maybe the only ones working on that, but it's interesting because certainly the nature of the dark matter is, for my question, and in the group using different technologies. Okay, I will finish it for now. Sorry to leave you to lunch. I would like to say this is our institute in Córdoba, was founded by Jose Luis Arce. After that, you are seeing Lamba, Jose Bosch. Right now is Nelson Padilla, Mario Barri was there, also Julio Navarro, Laura Sales, Ariel Sanchez studied there. A big group with a lot of interesting people to meet. I would like to invite you to visit us. We are just 1 hour from Santiago, 3 hours from São Paulo. We're very happy to receive you. We have an annual meeting, Fan of Fans, that we have all in April. It's in April because autumn is the best time of the year to visit Argentina, but also it's the time when the graduates finish their places. And we use the people that comes to the hub to evaluate the PhD thesis. We're very happy to receive. We have annual meetings since more than 10 years ago. It's an interdisciplinary meeting, but we're very happy to receive. If you would like, just send me an email and we'll contact with the organizers every year. I would like to thank the organizer for this wonderful workshop. Thank you so much for your advice.
Just reminding you that we have a discussion in the afternoon.
Oh, yeah.
About the local what?
I understand if you prefer to go.
Someone's very, yeah, so. We're hungry or good questions? I have a question. Well, Claudia had a question.
Yeah, but it's maybe in private.
Private. Okay, at lunch.
So having questions.
Lunch, you can ask questions to Maria. At lunch, you.
Okay, I will send it 2 weeks.
Okay, so let's thank Mariano again. When we get back, 2:15 or 2:30?
15 and then everybody will be here at 2:30.
Oh.
2:15, I think is the one. So we get back 2:15. I think Tiago is giving this.
If someone is interested on use this Angular mass tool, we could make a tutorial. There is examples on the web.
What was the program?
Tiago is MD anomalies and then.
What, 2 discussions? One's one. Okay.
I know you have to give us 5.